Bueno, 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 bueno. ¿Se oye? Ninguno. Ninguno de los dos micrófonos sirve. Ya. What is bueno? Bueno, 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 bueno.
Okay, we're there. Okay, so I know Pepe has been an inspiration to generations of young mathematicians and a mentor to them, but I met him when I was, starting to consider myself a senior mathematician, probably in my mid-40s, and for me, watching him, how he carries himself as a senior mathematician is an inspiration and a role model too. Everything he does for the community, it inspires me to try to do more. Okay, so let's get started. So I'm going to start with two classical theorems about closed hyperbolic surfaces, and then we're going to try to sort of see how those theorems might propagate into theorems about discrete subgroups of higher rank Lie groups, or if you prefer, just think about the example of complex Kleinian groups, which are discrete subgroups of the Lie group PSLDC. So X is going to be, and I know I'm a little off topic with the conference, so just yell at me if you need something defined, or if you can't read my handwriting, or if you just feel like yelling, that's okay too. H2 mod gamma. Gamma is contained in PSL2R, which we think of as the set of orientation-preserving isometries of the hyperbolic plane. Okay? And so you might have a surface that looks like this, and associated to every conjugacy class, so if gamma is a conjugacy class in the set of conjugacy classes of gamma, then there's going to be a geodesic gamma star. Okay? And the length of gamma star is exactly twice the logarithm of the top eigenvalue of gamma regarded as a matrix in PSL2R. Where here you're taking, the eigenvalue isn't defined, the absolute value eigenvalue is well defined. So if I was being careful, which I probably won't be for the rest of the talk, whenever I say eigenvalue, I'm taking the modulus of the eigenvalue, okay? And also sitting on this surface is a natural flow, which is one of the canonical first examples you study in dynamical systems, or at least in hyperbolic dynamical systems, which is the geodesic flow. So the geodesic flow lives on the set of unit tangent vectors to x. You take a unit tangent vector, and that tells you you're pointing in that direction, and if you're flow by time t, you walk t in that direction, and then you see where you're pointing. Okay, that's just the geodesic flow. This exists for all t, both positive and negative. And then there's a theorem which goes back to Hedlund, I believe, in the 30s, which says the geodesic flow phi t on the unit tangent bundle of a closed surface is ergodic. And what that means is that almost every vector goes almost everywhere on the surface, almost all the time. So more mathematically, it says that if A is a measurable subset of T1x and is invariant under the flow, then the measure of A is 0, or the measure of the complement of A is 0. So notice here there's There's lots of measure zero subsets which are invariant, and we see one right here. If you take the set of all tangent vectors to the closed geodesic, that's invariant under the flow, but it's a pretty small set. It has measure zero. And then this was generalized by Hop for closed and equally curved surfaces, etc. And then another theorem, which I think comes from the late 50s, though the approach I'm going to take to it comes from Margulis's thesis. So it's due to Huber. And that's maybe, for generalizations, put Bowen and Margulis there. That's Rufus Bowen, not Louis Bowen. And it says that if you look at the number of conjugacy classes such that the length of gamma is less than or equal to t, that's asymptotically e to the t over t. So if you want to prefer that, we could say the number of closed geodesics of length less than or equal to t is e to the t over t. And this is very strong asymptotic in the sense that the ratio of these two numbers goes to 1. Okay? And Huber did this using Selberg's trace formula, but Margulis had the idea to use properties of the geodesic flow, and so he uses to get his counting results, which aren't exactly the same as this, he uses the fact that geodesic flow is mixing, which is another stronger property than ergodicity, which I think I want to kind of ignore. Okay. Questions? Okay, well that was all well and good, but if you're like me, and what you really like is infinite volume hyperbolic manifolds, not closed volume hyperbolic 3 manifolds, this whole thing kind of dies, even in a very simple case. So what's the simplest infinite volume hyperbolic manifold? It's just you take a Schottky group. These are, well, let me try again. Imagine this is a symmetric picture, and you pair this side to this side, and that side to that side. And then you take these unique common perpendiculars, they will all kind of glue up. So notice this is the gluing pattern, top to bottom, left to right, is just the gluing pattern of a torus. So what you get here is a torus with a hole, and geometrically, this surface looks like this, and you have some closed geodesic here, like that. And this is often called a funnel. It's like exponentially expanding. It looks like 4 of these little chunks between lines glued together. Okay, so you can see, they're like that, like that. Now, almost every vector just goes to infinity. So this is not so good for dynamics. For almost every v in the unit tangent bundle, phi t of v leaves every compact set. As t goes to infinity. So once you escape, there's wide open spaces here. Once you get out here, you just keep going and you're lost to infinity. So that tells you, but we know there is some interesting dynamics here because there's a bunch of geodesics which remain inside that never cross this geodesic. And those are kind of, they look like they're behaving just like on a closed surface ergodically, but this measure, but Lebesgue measure on the geodesic flow doesn't even see them. So luckily Dennis isn't here for me to give the ahistorical motivation for Patterson-Sullivan theory. So for me, the motivation of Patterson-Sullivan theory is how do we see this dynamics? So the interesting set is sometimes called either the recurrent set or the non-wandering set, the set that doesn't go off to infinity, is all G of E6, both of whose endpoints are in the limit set. And then modded out by the group action. So if you know, I'll maybe say more about this later, but I'm going to give a long overview, which might end up being my whole talk. So I'm hoping I can at least communicate the overview. T1 of H2, you can write it as boundary of H2 cross boundary of H2 minus the diagonal, because all G and E6 join different points, cross R. So this is the endpoints of the GSIC, and that's just how far along you are along the GDSIC. And there's various versions of the hop parametration to make it precise. So in this sense, it's the set of the G and E6 which join points in the limit set cross R, modded out by the group action. Is that okay? So now we want to kind of understand this set, because dynamics which just goes off to infinity is not very interesting. So what Patterson did in dimension 2, and then Sullivan generalized to higher dimensions, was to construct a measure supported on the limit set. So now, and we're going to use that measure to construct a measure on the GSIC flow, which is supported on this non-wandering set. So now it's seeing, this measure sees the dynamics, unlike Lebesgue measure. So you define a Poincare series associated to the group, and that's summation over the group, e to the negative s, distance from 0 to gamma of 0. Okay? And you know by the root test or something that there's some critical exponent where below that exponent it's infinite and above that exponent converges. So there exists delta gamma, which is the minimum. In general, I'm going to be interested in the case where it's the minimum, but in general, it's just the infinite s such that this series converges. Or so you could think about this. This is the exponential growth rate of the orbit. If you look at the number of orbits of the number of orbit points within T of the origin, this is the exponential growth rate of that number. And if you can sort of see, that's pretty closely related because this is distance to the origin. Okay? And then what he does is, or what they do is they construct measure mu on the limit set which behaves like delta dimensional measure. So now delta is typically some random number between 0 and 1. So what does this mean? Well, how should it be? It should be that if you, is that the push forward or the pull back? If you look at the action of gamma, the difference is gamma inverse, is the gamma inverse prime of z. So if you look at a point z and you compare gamma star mu to mu, the difference is exactly a derivative raised to the power delta. So for instance, Lebesgue measure is a measure like this where delta is 1. So if you're looking at if the gamma is a closed surface group, this is just going to be a funny way of constructing Lebesgue measure. But in general, for this, delta is going to be less, this group, delta is going to be less than 1, And now we've got something interesting going on. So one of the first things you can prove, and I should have looked up. I don't know whether Patterson did this before Sullivan or not, but it's part of their whole theory, so let's put both their names down. If you look at the gamma's action on the limit set with respect to mu, this is ergodic. So it says it's mixing things up quite a bit on the limit set. The action of the limit set, everything goes everywhere all at once. Okay? And then you use this to construct, you use mu to construct a measure on geodesic flow on T1x, which is supported on the non-wandering part. Oh. So now we're going to want to get a measure on our geodesic flow, which completely ignores the trajectories which go off to infinity. Okay? And on the non-wandering part. Or if you prefer the recurrent part, some people, there's a difference if for a finite volume surface, but there's no difference for a closed surface, so I'm sort of okay.
Theorem also says that beautiful averages converge to this measure. Does this have a property of this in that sense?
Yeah, I think so, yeah. Okay. And it has this simple form. It's now called a Bowen-Margulis-Sullivan measure. Because it turns out this measure, and I don't want to go into this, but for people who know it, this might provide some context, is a measure of maximal entropy for the geodesic flow on T1x. And Bowen and Margulis had their own constructions of one before Sullivan came along and gave this other one. And it just has the form, well, you think, entropy here is the exponential, is delta is going to be the entropy. Yeah, but that's kind of an aside. If you don't want to know what a measurable maximum entropy, which I didn't know 3 years ago, don't worry about it. I'm not going to emphasize that in the talk. But if you've seen that, that provides context for this, I think. And measure, you first build it on the universal cover, and you want to go, oh, it's d mu, dt. This is a measure on the boundary, measure on the boundary, cross the measure on the flow lines. But, you know, mu is not invariant, it's only quasi-invariant. So you need a correction factor. So it's e to the delta g. There's some function called the Gromov product, which you can, you know, since you know how mu behaves, you know exactly how to figure this out. I could write down the formula for you later, but that won't matter for the moment. And then this is gamma invariant. So it descends to m. And it's a measure on the full geodesic flow, but again, it's just supported on the non-wandering part of it. Okay, so then Sullivan shows that that the geodesic flow, there's still a geodesic flow, Vt, the same one, on T1x. This is ergodic on T1x with respect to this measure he's constructed. And so the point is, if you just restrict yourself to the geodesics which don't wander off to infinity, then you see all this ergodicity that you saw everywhere in the closed hyperbolic case. And then Sullivan had something like this. The version I'm going to state, I can't find an earlier mention than Roblin. Roblin very much implements the technique of Margulis's thesis, and he says that the number of conjugacy classes, which again, a conjugacy class we can just think of as a closed geodesic, where the length of gamma is less than or equal to t, well now it grows like e to the delta t over delta t. So originally I should have written e to the 1t over 1t for Huber's result, right? And so now you have this kind of beautiful counting result which tells you about the periods, how the periods of your geodesic flow grow. And even, so this used this measure, but here this statement has nothing to do with that measure, right? This is just a statement about the number of closed geodesics on the quotient surface. That's all it is. And so all this stuff that I said here works absolutely exactly the same for HN. Okay, and so you get all these same results. I need finally generated here. Sorry. Nothing true about infinitely generated groups. Right? And in general, when you generalize it to higher dimensions, you need the condition of geometric finiteness. Okay. But it's a nice property of PSL2R that every finally generated subgroup actually is geometric finite. Of course, I spent the first 25 years of my career exploring the fact that that was not true for PSL2C. So I guess I should be glad it's not true. I would have been out of a job. Okay. So what I want to tell you about then is some work. You know, there's been sort of a movement, and you see it in the last 20 years, you see it, a lot of people doing it in different contexts to try to understand discrete subgroups of Lie groups by analogy with discrete subgroups of isometry groups of HN. And so, you know, Pepe's school studied complex Kleinian groups. There's a whole school of Benoit where he studied closed projective manifolds and their geodesic flows. Hitchin representations were introduced by Hitchin, and this all happened about the same time, right around 2005. All these kind of disparate things were going on, and they've all kind of coalesced in the notion of an Anosov group. And let me just not define an Anosov group, but let me tell you about some complex Kleinian groups which are Anosov. And so Anosov is one candidate for what it would mean to be a convex co-compact complex Kleinian group. So the simplest example, so this is an Anosov complex Kleinian group. Would be a complex Schottky group. So if you let A and B be elements, or doesn't really matter. There's no. I always forget there's any difference between SL and PSL. For this discussion, there really isn't. And you take them in. If A and B are generic, you can take powers of them. So A and B, I want them to be loxodromic, which means each of them is diagonalizable with distinct eigenvalues, and moreover eigenvalues of distinct modulus. So sometimes that's called strictly loxodromic. And then I would like that all their sort of attracting planes in all dimensions are transverse to each other. So if I take any, like the maximally attracting 2 plane here should be transverse to the D minus 2, the maximally attracting D minus 2 plane here. And so remember, the maximally attracting 2 plane is as you're just spanned by the eigenvectors associated to the top 2 eigenvalues. Okay, and so if you do that, take anything like that, then there exists some n. You can place conditions on what this n needs to be, such that this group, an, bn, is a complex Schottky group. And that this will also be an example of a Nosov group. Okay? I can say a little, yeah, at some point you could just, if you want to direct me to do different than I'm doing, that's fine. I know the crowd loves, I guess Dennis is gone. Usually the crowd loves to direct the speaker to do different things in this group. Yeah.
So this is sort of virtually group or something?
You know, it's going to be a free group. So, complex Klein group was defined earlier, but this is a discrete subgroup. This is complex Kleinian and a Nosov. So it's certainly not true that every complex Kleinian group is going to be a Nosov or relatively a Nosov. Even for regular Kleinian groups, you're a Nosov if and only if you're convex co-compact. You're relatively a Nosov if and only if you're geometrically finite. But I mean, I think it's kind of an interesting, as far as I can tell, unexplored direction, what the analog of convex co-compactness and geometrically finiteness are in the complex Kleinian setting. And one option is to look at the notion of Nosov, or really Nosov. Okay, and then you have, we've also heard about R-Fuchsian groups. And we heard earlier about C-Fuchsian groups. These were subgroups of PU21, which were kind of convex co-compact subgroups of PU21, and then you regarded that as a subgroup of SL3C. One really nice thing about the notion of a Nosov is that it's stable, meaning that if you make a small deformation of a Nosov group, it remains a Nosov. So you can take anything R-Fuchsian and C-Fuchsian and living in PUT1, and you deform it a little, and now all of a sudden it's risky dense, and it's outside PUT21. And those groups remain covered by the theory of a Nosov representations. So here's relatively a Nosov allows for the possibility of parabolics. So an example of that is, suppose you have sigma from a free group into PSL2R, and then H2 sigma of Fn has finite area. So this is a finite area hyperbolic surface. Okay. Then it turns out, again, something I learned only recently myself, because I'm not from this higher rank Lie groups world, is that there's a unique, given any D, at least 3, there's a unique representation from PSL2C into PSLDC, which is irreducible, meaning the image doesn't preserve any sub-vector space. Right, so if you're me, I know how to put PSL2C into PSLDC. I just put it in the upper left-hand corner. That's not what they mean. This is you put it in irreducibly, and that's unique up to conjugacy. And then if you look at tau D compose rho, this is relatively an Nosov. And the key difference here is a parabolic element has gone to a unipotent element of PSL2DC, which has a single Jordan block. Okay? And so small deformations of tau d compose rho
That representation is a kind of pitching representation.
Yeah, this is, sorry, I was, yeah. So this is, so Hitchin studied this in the case when it was a closed surface, and this is another one of the first big, this is actually how Anosov representations were discovered. He had discovered that this was a component of representations into PSLDR, which was a ball, just like Teichmuller space. So he called it Teichmuller component, and he asked the question, what does this mean geometrically? Is this special or is this just accidental? And Francois Labrie developed the theory of Anosov representations, and he showed all Hitchin representations are in fact Anosov. So in particular, discrete faithful, and kind of convex co-compact in some higher rank sense. Oh, sorry. Sigma rho equals rho, preserving the unipotency. So, you know, when you deform Kleinian groups, you often want to keep parabolics parabolic. And so you want to keep these unipotents unipotent. But there are many deformations like that, and those give you, again, a family. These, if you look at just the Hitchin ones, they lie just inside a copy of PSL2R. So nothing new is happening there, but then if you wiggle them, all of a sudden, you don't know what's going on, and that's something to study. Okay, so I think I'm just going to get to the end of my overview. So there's been also a development of Patterson-Sullivan theory for higher rank Lie groups. The first people who did that were Albuquerque and Jean-Francois Kent, which I apologize to all the French people in the audience for how I said that. But they worked in the general concepts of discrete groups, so you probably can't, you could get some aspects of this, but you really couldn't recover all of the stuff that I wanted to recover. So the first person to really study from this viewpoint was Andre Samborino, and he worked in the relatively Anosov case, and the stuff I'm going to talk about is joint work with these people in the relatively Anosov case. And you should think, why is this more difficult? Well, if you think about it, studying dynamics on closed and negatively curved surfaces, it took many years to figure out how to generalize that to dynamics on finite area negatively curved surfaces, because dynamics really loves a compact flow space, right? And whenever you get non-compact, it starts getting nervous. So the justification for doing this is that the techniques Andres used, which were based in the so-called thermodynamic formalism, don't work. It was based on the fact that geodesic flow was modeled by a finite Markov coding. And that's not even true for a finite area hyperbolic surface. This geodesic flow is only modeled by a countable Markov coding. Okay, so let me tell you the theorem. So first of all, the question is, what should our notion of length be? And just for my, okay, so I'm going to work in, I think this is the most natural context for complex Kleinian groups, so-called P1 relatively Anosov. So when P1 relatively Anosov groups, you look at the limit set in the flag variety consisting of 1 planes contained in D-1 planes. So whereas in complex Kleinian groups, much of the work on the limit set has been on the D-1 plane. For us, it's very useful to have both the 1 and the D-1 plane. And again, that's another kind of connection I would like to understand better about between Anosov and the complex Kleinian groups community. Well, there's many notions of length. in this setting. I could take phi equals log lambda 1, just generalizing in hyperbolic space. Another thing that generalizes, or phi equals log lambda 1 minus log lambda d. That's also basically just hyperbolic length when you restrict it to hyperbolic space, or, you know, phi equals a log lambda 1 minus b log lambda d. B are positive also work. And some other things might work. Anything, any linear functional which is positive on the Benoit limit cone, just to say it out loud. I don't have time to define that. So what did Samborino do, and what did we complicate? What did we generalize? Samborino. I think this version just needs CZZ. But then there was subsequent work by Kim and O, and there's also extensions in my later work, as there exists a flow space Y Vt such that closed orbits are in one-to-one correspondence with conjugacy classes of loxodromic elements of gamma. So here, I didn't set it. Gamma and PSLDC is my group. So you've got a flow which behaves like the G-sig flow. Every element has a period. Every element has a closed orbit, and then the periods are in one-to-one correspondence with phi of gamma. Well, gamma is the loxodromic element. So it's just like the G-sig flow. The set of all closed orbits of a G-sig flow to the surface is the set of all closed geodesics. The period of a closed orbit of a geodesic flow is exactly the length of that geodesic. So this says, if I have something P1 relatively docile and a well-behaved notion of length, I can create a geodesic flow. And this is it's metric anosov in some sense. It's not smooth, so it's not really anosov, but it has a held or well-defined notion of strong stable and strong unstable manifolds, for instance, which is kind of a good, that's kind of the minimal thing you need to start doing hyperbolic dynamics is held or strong stable with held or strong unstable manifolds. And moreover, this geodesic flow is ergodic. So again, this is sort of some nice object, and its periods or lengths. So this again thinks, oh, I can try to implement this Margulis strategy where if I have a mixing geodesic flow, I can count the number of lengths in terms of some sort of entropy. And well, that exactly works.
You still have the series.
Yes. Right.
You can construct a with that.
Right, so how would that go for a complex Kleinian group? For a complex Kleinian group, Q gamma S equals the summation gamma and gamma e to the negative s. And if I'm using lambda 1 as my notion of length, then this is going to be sigma 1. or log. I think log sigma 1. Sigma 1 gamma is the operator norm of gamma. It's just the first singular value. Okay? And then, so singular value. So if you want the distance from the origin hyperbolic space to gamma of 0 is exactly log of the singular value of gamma. I worked in Kleinian groups for 30 years. I never knew that fact. But in this fact, this is very relevant here. And so that you do this, the construction of the Patterson-Sullivan measure, if you know it, I was going to give it, but I don't think I have time, is very simple and exactly the same as what Patterson did. It's basically an 8-line proof, which you just got to set up. If you set up all the analogies of the language, boom, it just pops out.
And the critical exponent still gives some information on the geometry.
So the critical exponent is going to be, with respect to, here, some BMS measure, right? I didn't tell you what measure was on this, but you can, again, use the Patterson-Sullivan measure. You just do the exact same construction of the Patterson-Sullivan measure. You now have to figure out what your correction factor is. That's called the Gromov product, and then boom, it all goes through. And you know what's even more disturbing? I have a French co-author, and so what would you do if you were French? You would say, what are the most assumptions I could remove, right? So, in fact, in this paper, we work with just a discrete convergence group action, which has a cycle. And then you construct a Patterson-Sullivan theory. So there's no real geometric space there at all. And shockingly, all of Patterson-Sullivan's arguments just kind of go through. And we can even get mixing results with a few more, mixing and counter results in that setting with a few more assumptions. So the thing I'm about to state in the relatively Nosov case is actually not done the way Sambrino does by doing something which is kind of directly related to the symmetric space. It's done in this abstract setting because we couldn't figure out how to do that, basically. So other theorem, and this is again due to Sambrino in the Anosov case. It uses work, my work with Zhang and Zimmer, but it's proven in this final paper, which says in the same setting that if you look at the number of gamma in gamma such that beta gamma is between, here, that's bigger than 0, I throw out the parabolic. I'm throwing out the parabolic and unipotent average. They have length 0. That's a sneaky way of throwing them out. This grows just like e to the delta. There's some critical exponent, e to the delta of gamma over delta of gamma t, there we go. It's the exact same result holds. And one more linkage to this group. In this paper, we need to check the conditions that we get here in the abstract setting. One of the conditions is to understand how does the Poincare series of a subgroup of a subgroup of a semi-simple Lie group, or PSLDC, let's say, which is weakly unipotent, meaning all the eigenvalues of L have modulus 1. You need to show that in that case, this expression diverges in its critical exponent. And that used Hironaka's resolution of singularities. Please don't ask me to explain how. That seems like a good place to stop.
Any questions?
Yeah.
If you take A and B to be just real numbers, like different kind of arithmetic properties of this, do you get some similar results for the Poincare functions?
I mean, so this theory, this is a result of about P1 relatively Anosov subgroups of any semi-simple Lie group. So, and in fact, most of the attention has been to subgroups of PSLDR in the Anosov world, or more into real Lie groups. And so Yeah, that's why I think there's kind of a lot of possibility for interaction between people more interested in the complex Kleinian world and the Anosov world, which is so far kind of focused on the real setting. I don't know, sorry. I don't know anything about automorphic forms in H2, so I apologize.
It looks like you interrelated the center space ordinals. I mean, if you take an arithmetic group, can you get some arithmetic theorems like
Yeah, this.
from the Dirichlet series,
Yeah, I don't. If Dennis were here, he might have some idea, but I don't see how this theory interacts really with arithmetic, in the sense that it's very much a purely dynamical theory. Now, I guess there is an interaction which comes from there's a zeta function, right? Yeah. So maybe if you start with an arithmetic, I'm out of my league here, but maybe if you start with an arithmetic group, then you would end up. But so also lattices in higher rank don't fit in this world at all. They're not an Anosov or relatively an Anosov, but you could still maybe take a subgroup of a lattice which was an Anosov, and then hope that the arithmetic of that group kind of got reflected in the zeta function. But yeah.
you think this suspension that you talk about in the PSL, then you have coordination, projective value of the surface. You have a representation of the
Right. So the original
so you got the properties of that relation.
Yeah, so actually, I'm not sure this is exactly what you're thinking of, but what it reminds me of is Labourie's original definition of Anosov. He looked at the flat bundle associated to a representation over the geodesic flow. And then he looked at a flow space. And so being P1 Anosov means that that flow space has a splitting into a line bundle and a D-1 bundle, such that everything in the line bundle is contracted more than everything in the D-1 bundle as you flow. So it's kind of like it's like a dominated splitting kind of thing.
Yeah, you have the geometry of foliation. Thank you.
What about the transfer operators associated? Because you said some of the people that were using thermodynamic formalism, right? I believe it was Zimmer.
No, that's a different Zimmer.
Yeah, but are there any transfer operators associated to this?
Well, in the Anosov case, yeah, the Anosov case there should be, because then you have a finite Markov coding, so maybe that. In this relatively Anosov case, you don't know you have a coding, and if you did, it would be countable. Okay. So,
but
actually, the
first.
first.
A countable horseshoe.
What?
It's a countable horseshoe anyway.
Something like that, yeah. Yeah, we were able, so in the case of these Hitchin representations of binary groups, we're able to redo all the thermodynamic formalism we needed with the countable Markov shifts.
Both of them, or in both of them?
That's actually with Bray. We did that with Bray, Harry Bray, Giuseppe Macau, who's a student of Francois Le Drapier, and Giuseppe Martone. Yeah.
Great. Thank you very much.
Sure. Agua caliente?
So like,
Let me give it a try. Nope. Yeah. up there? Okay. Gracias. My talk was going to be after this line of everybody, but then you nicely set up all sorts of things for me. So yeah.
Hi, Zach. How are you doing? Good to see you. Right. Oh, that's been a little bit weak, but I think okay. Do you need I give you some extra credibility? The drink that I. Ah, no. Do you need? I'm back to water. No, that's pretty nice. But let me try your.
Donde no lo roce mucho, y está aquí en la solapa. Aquí yo creo. A ver, habla.
Onde que Onde que
Ahí está prendido ya.
já tá ligado, ok. Alô? Alô?
A ver, habla bien ahorita.
Así que
Sin agacharte.
Assim que sou.
Yo creo que más, un poquito más arriba.
Bom, isso, ok. Muitas graças.
E aí? Tudo bem? Sentei seu... Pode ir.
Aurélio não vi se está cara? Não.
Mas a gente, como já conhece a história, tá tudo bem, tá bem.
Começa a história da torcida que...
É, a torcida vai faltar, vai passear. Você consegue uma garrafinha de água pra mim? Consegue uma garrafinha de água pra mim? Um copo, pode ser, só pra botar.
eu consigo daqui
Vai
a
ser?
pouco, mas pelo
Quer que
momento
assine?
a gente necessita que você assine.
Assinar primeiro.
Copo de água fria ou quente?
Frio. Só pra... Acho que não tá escrevendo. Acho que eu tenho caneta ali. Pega. Sim. Olá.
Desculpa, não. O negócio é que precisa ficar um encendido, mas outro não. Bueno. So, welcome back to our session. The next talk is in charge of Professor Raimundo Nonato dos Santos, Araujo. And he's going to talk us about the minus boundary of the real singularities. Joint work with Pepe, Aurelio, and Ribeiro. Muito obrigado.
Thank you. Okay. All right. Thank you very much, and thank the organizer for accept my talk, and also thank for all the very well organized meeting, very nice meeting. So, okay, I'll talk today about a project I started with Pepe, Aurelio Menegon, he's not here today, I think, and a former student called Michael Ribeiro. So, unfortunately, I needed to review some definitions and notations that several speakers have already presented here, Professor Juan Nuno Ballesteros, Aurelio, and so on. But okay, I will be very quickly in this beginning just to save time. I work this presentation, I will always consider analytic map germ from Rm to Rn under this condition. And I will represent the germ and the representative of the germ by the same notation, okay? This is very common. And also I will consider, when I will consider some sets, I will consider a set of germ at the origin. So the zero locus of your all mapping, I will denote this way. The singular set is the standard ones, and this notation is for Jacobian matrix of our mapping, or of representative of the mapping. And the discriminant set is just the image of the singular set. And I will consider today the case that we say isolated critical value at the origin. It means that discriminant set is only the origin. I will consider actually two cases, okay? The case where the discriminant, the dimension of the discriminant set is positive, but it will be a very special case for me today. But most of the talk I will concentrate in this situation, okay? It's not hard to provide example, to build example actually under this condition, okay? So the singular, so it means of course that the singular set is include the variety. General remarks, so our analytical map will be considered, of course, has a non-constant function. And as I said, our set map will be considered as a geometric theory. So what is the monotube vibration? I think Ballesteros already, Ballesteros already mentioned about this, just to review. So we say that analytic map germ F from Rm to Rn admit a called monotube vibration if there exists epsilon 0 and eta under this condition, such that in the closed ball centered at the orange, we have that this restriction to this set is a smooth locally trivial vibration. And also we ask that the diffeomorphism type does not depend on this choice. So this way we can set a topological data. So this will be a topological data that we can assign to the singularity. Okay. So I think the talk of Ballesteros, also the talk of Aurelio, they were trying to explain a problem concerning these things, because it is not true that if you just consider a map of germ, fix, for instance, the singular set, the image will be well defined and has a germ of set. So you have to be careful about that. It's a very old problem, but maybe nobody have talked about that. I have read several papers that people are doing things just if everything is very well defined. But anyway, under the condition I will work today, I will show for you today, this is not a problem, okay, of course. And in both cases, discriminant positive and discriminant, the dimension of discriminant positive and dimension of discriminant 0, which is more clear in such a case. So that's the standard picture, the monotube. So this supposed to be the closed ball, okay? And we can prove that, of course, I will show you two conditions that assure the existence of such a two vibration, but that's the picture that we consider, okay? So, I mean, the picture of such a vibration here, okay? So, this is the punched ball in Rn, and this is a closed ball of a radius small enough, and you just put this punched ball here, you get some things like that, like a full tube. And the restriction of your map to this full tube, of course we remove the variety here because we remove also the orange. And this restriction is a locally trivial smooth vibration. The point here, or the main data today I want to focus on, is the boundary of the neurofiber. Okay, this is what I'm concerned today. So to state the existence of the tube vibration, we need to introduce some standard notation definition. For instance, the monoset, which is the monoset. What is the monoset? So maybe I don't know if I took the correct slide, but anyway I can fix. I already exchanged that today, but I can fix anyway if any problem comes. So the problem, so the condition here, we just consider a neighborhood of the origin, and ρ has a smooth non-negative and proper function that 0 only at the origin. We say that ρ defines the origin, okay? And for instance, the square of the distance function to the origin. So in this way, so I didn't fix it here. So suppose that I work only for the square of the distance function to the origin, okay? So sorry for the last slide. So anyway, so I mean, we can consider such the definition of this set, just plug here a whole function, as I said before. But I will fix a whole as the square of the distance function to the origin, okay? So in such a case, how we define the color the minor set or the polar set of F relative to E is the singular set of this pair. Okay, so it is easy to see that the singular set of your map is included here. It's a very easy exercise. And in the complement, what we get? We get the points where the fibers are non-singular, but it is transversal to a sphere of some radius in some point. Okay, that's what this kind of set is captured. Okay, among your mapping. So let us remind again the tameness condition. We say that real analytic map germ from Rm to Rn is tame if we get such a kind of condition. I think Aurelia also called it the tame condition, right? I think you work in a very different, the definition of your polar set is you define a very different way, right? But anyway, the idea behind the kind of things you want to do, maybe keep the same idea of such kind of, we say, transversal, right? So anyway, we say that a map is tame if a germ offset at the origin, and that's the picture for the tame situation. So this blue line is supposed to be the variety. The green line is supposed to be the set. You may have some component of this green line inside the blue line, but anyway, outside the blue line, it's possible to find a kind of horn neighborhood of the variety, which such a neighborhood does not intersect VF. Sure. The variety of your map. Okay? Okay? Could you move? Okay. So, who is what? Yeah, so maybe I change. The same notation, right? VF, V, VF. Okay, so that's the idea behind such kind of tameness condition. And so several mathematicians have been working with such a condition. For instance, David Massey, Pepe, Cisneiro, Jawad Snooze, Aurélio, Mihai Tibar, and Pichon. This list is not complete, sorry about that. Ing Chen, Griffin, Delbert Breeze, Hansen, he worked with that when he was supervised by Brodersen in Oslo, University of Oslo, and Osamu Saeki, Tassiana Souza, Inak Zapata. The list is very big. Arnaud Baudin, I think Popescu Popu as well, right? No, but I will send I will show a reference. I will show a reference that anyway for sure is yours, but we can. But anyway, so this is a very common condition to consider when you are trying to understand the topology, geometry of the singular set by looking to the fibers which is closer to such a set, such a singular set. It's a very common situation, but no problem. So some very well-known examples is the tone AF irregularity along the fiber. I think Ballester already reminded such a definition. But tone implies such a condition too, but the converse is not true. Okay, I will show my example today. What else? The ICES, isolated complete intersect singularity. It also satisfies such a tameness condition. And the singular set here is not included on V. So such a condition, such a tameness condition, does not to do with the isolated covariance. Okay, this is different conditions. These are different conditions. Okay. So what else? So simple L map, in particular harmonic morphism, and so I will show just only two references concerning that. One is by Ribeiro, where he constructs several examples with certain condition which is not does not satisfy the tone regularity, and also this example right here. Okay, in such a paper right here. Such a paper is very interesting because he constructs a mixed map. Most of the previous example which was done by mixed functions. So now he considered the more general case. Okay, so I will use today an example which was showed in the reference file. So existence of the monotone vibration. So let F as before, and under the isolated critical value it tame. Then it's possible to prove that F admits a monotone vibration as well. Okay. So corollary, if we just put back the spheres inside that ball in the target space, when you put back that, you also have, of course, by restriction, you also have a vibration. Okay, it is also called the monotube vibration, but in the empty tube. Okay, so that's the standard picture as well. This is the sphere. When you put back that, you get such a tube here. Of course, the interior here is empty. We just put this one just as a reference. Okay, and now, when you take a point here, the fiber will be here in that empty tube. Okay, so let's now move to the composition of singularities. So now consider such a diagram. Now we have a composition of two map germs, F and G, I will call H. And it is easy to see that the variety of 8 is given by the pullback of the variety of G. And by the chain rule, we have such a description for the derivative of H, which means that from that we can conclude that the singular set of H is included here, union here. Okay. Therefore, if the discriminant of F is 0 and also the discriminant of G is 0, immediately we get the discriminant of H is 0. So, but what to say for the taming condition? Is it true that such a condition is preserved by composition? What the guess? No. No. Really. But it was not easy to find a okay, so the answer in general is no, but we were able to characterize such a condition here. It's a very recent paper. And concerning the determinants of compositions, we proved that so if we consider F tame with discriminant 0, and any G, doesn't matter, G does not play any role in such a situation. If you ask such a condition for F, then the composition is same. If only if we have such a kind of transversality condition, but now involve the image of F. Okay. So that's what to us. It was not too easy to find such a characterization. And but anyway, of course, we should anyway see how such a terminus condition would be related with the singular set of G. But it was not easy in the beginning to see how we should consider that. But anyway, by the end, we were able to, after we have checked some simple example, we were able to consider such a condition. Finally, we were able to do a proof. So what does it mean? It means in particular that if the singular set of G is empty, or G has a isolated critical point at the origin, in these two special cases, is the composition is tame. If you ask, of course, that F is tame and discriminant of 0. This will be one of this case I will consider today. Recent results on the boundary. Okay, now let's move to a recent paper written together with Pepe and Aurelio. Aurelio is right there. We were worried. We didn't see you when the talk started. Okay, but thanks for coming. So anyway, just consider such a diagram now. Okay, so this is, I changed the notation. Okay, now instead of big F, I map just the notation. Okay, because I will reserve the big F for the fiber. Okay, for the notation of the fiber. And now take here the projection in the, let's say, y first coordinate. Okay, and you can project now in the other direction to the k minus y remainder coordinates. Okay, so if you do this way, you take here, you get here a map which we define as fy, and here fk minus y. Okay, so for the mean of fibers, once they exist, I will consider the mean of fiber of fy and fk minus y by this notation. Okay, f under f under y, f under k minus y. Okay, all right. So we were able to construct such a big diagram here. Such a good diagram was very nice to us to get it because it relates all the minor set, all the singular set of the map, the projections, the minor set of your maps and projections, and also the minor set of the F modulo, the absolute Fy or Ff or Fk minus y over absolute the absolute value of the function. I mean, of course, in the complex case, the case of functions, it's called the argument function. Okay, so that is very nice because we could see this way that all the arrows comes to this set, the minor set of F. It contains all information about the projection. That was very nice to understand in the beginning. Maybe it was, I haven't seen such a diagram written before. Maybe it's very well known, but it was good to us to get such a picture. So what was our first result concerning the boundary? We were able to prove that if small f is as before, I mean tame and with isolated critical value. If we consider any I between less than k and greater than or equal to 1. For any index this way, we are able to prove that all the projections, they are tame and also has isolated critical value at the origin. So we have minor vibration for everything, for all those mappings. And the boundary of Fi, the of I. What? Those two conditions, tame and isolated critical value. It implies that all those mappings, all those projections, or those composition after projection has the same property. Okay. So what's the point here? We were able to prove it is not. I mean, somebody else have already proved that. I think it's Seade in a paper. He already did. He already proved a result like that. But for us, it was very easy to get such a result. That was the point. Okay. So let me just read the statement. So under F. Tame with isolated critical value at the origin, we are able to prove that the boundary of Fy the boundary of the minimum fiber of Fy, which I denote this way, is obtained by gluing together the two disjoint copies of the minimum fiber of Fy plus 1. I put here y because we are allowing that can be k. Okay. So the point is that for any possible index that you get here, once you consider such a projection and project again, project to get such a condition boundary of the minimum fiber. Okay. And what else? We were also able to prove that is again f under the same condition. The boundary of the Fy admits a kind of generalized open book decomposition according to our definition, given by the boundary of the minimum fiber of F. Moreover, if we have y such that k minus y is greater than or equal to 2, and the minimum set of such a projection here is empty, then the projection of the generalized open book can be given this way. This was very nice to us because there was some result concerning that for the ISIS case. And also a paper, we were able to find a paper by Popescu where he will, okay, I'll show such a reference, that when he was doing kind of a little bit more general situation in complex case. He will consider a complex variety with isolated critical point at the origin, intersect that with the sphere, if I understood well. And we're able to prove that under some boundary, it's possible to get such kind of open book. Yeah, for the contact structure. Yeah, so what else we were able to prove several formulas relating the boundary of the minimum fiber, the minimum fiber itself, and the sphere, the characteristic of all the things, and also we were able to prove some kind of Le-Gruel type formula, showing that the difference between the Euler characteristic of the boundary for two consecutive projections is equal to this guy. See, if you see here, the minimum fiber is the characteristic of the minimum fiber is obstruction. Okay, if you wanna consider the problem when the boundary of your mapping and the projection, they are homotopy equivalent. Okay, all right, I'm almost done. So, and Li plus 1 is the link, the intersection between the variety and the sphere. Okay, so we were also able to get the same kind of formula. So it seems that somehow, in such kind of singularities, the things behave well somehow. Doesn't matter if you are considering the boundary or the link. And of course, the Euler characteristic, okay, for the Euler characteristic number. And what else? Projecting twice, you have some hope to have the boundary, respective boundary, homotopy equivalent to each other. Okay, there is some hope. So anyway, Pepe, feliz cumpleaños, muchas gracias, thank you, obrigado. Is that it?
Any questions? Nope. So thanks again.
All right. So anyway, I am open if you want to discuss. So I forgot to write down the reference of Popescu, but anyway, I can send for anyone if you want to take a look.
Thank you. See you in next minutes.
Foi bom ali? Foi muito bom. Beleza. Eu vou te mandar a referência da tese do aluno que eu te falei, que aí você passa para o senhor. Tá bom? Tá comigo.
Desculpa, a gente está fazendo projeção pela internet, então aí você precisa de associar.
Aqui, vamos prestar aqui. Eu pego uma, quer que eu pegue uma?
então não vou poder ficar na sua palestra, mas vou apresentar você.
Tá bom, combinado.
Vamos sentar. Porque você precisa por cima.
Pode ser? Vamos ver. Esse aqui. Ele deveria assustar. Tá bom.
Pronto, dá para fazer uma prova?
Dá. Teste.
Tá pronto, muito boa sorte.
Obrigada.
Vou chamar a galera.
Tá bom. Sim, por favor. Obrigada. É Uberaba, Uberlândia. Não é muito longe de São Carlos, 3 horas de carro. Isso. Mas a universidade fica em Uberaba.
Hello, everybody. So let's continue with the next talk of the day. For me, it's a pleasure to introduce Professor Helen Santana. She's going to talk us about the geometrical information encoded by the Euler obstruction map. Thank you very much, Helen.
Thank you, Angel. Buenos dias. Good morning, everyone. This is my third time here in Cuernavaca, but it's the first one not only as a speaker, but also in a conference honoring Professor José Seade, who has a deep influence in my research. So I'm very happy to be here. So I thank the organizers for the opportunity and for all the effort to put together such a great conference, right? So thank you very much. I want to talk about the Chern obstruction with you, but first I want to tell a little bit about how I got into the Chern obstruction, all right? So for that, I need to define the local obstruction, which is something that you have heard yesterday in Thais' lecture, right? So today we are going to see the definition, all right? For that, we need a diagram that we are going to construct together. So I'm starting with a complex analytic space. Complex analytic space. D will be the dimension of this space. And associate, let me say that the ambient space of this complex space is U in Cn, all right? And I'm going to need the Nash modification of that space. So a map from the regular part of X to this Cartesian product. So over here we have the Grassmannian manifold, all right? So to each regular point, we associate a pair given by the point and the tangent space at that point, all right? So the Nash modification would be the closure of the image of this map. It's called the Gauss map, but we're going to use it. But this is the definition of the Nash modification. So an element in the Nash modification would be a point, would be singular, right? And we can consider a sequence of regular points converging to X. Let me just put it here. So a sequence, not pretty, right? Let me put a little bit up. So we consider a sequence of regular points converging to X. This sequence gives us a sequence of tangent spaces. So we look at each tangent space, at each element in the sequence, which converges to an element in the Grassmannian manifold. So an element in the Nash modification will be X, possibly singular points, and this limit of tangent spaces. All right? So what we have here is our space X contains in U, an open set in Cn. We have our Nash modification, which is in U Cartesian, the Grassmannian manifold. And we may consider an extension of the tautological bundle over this product, right? So an element in this bundle would be a point in U, an element in the Grassmannian manifold, and a vector V in that element. All right? So here we have the projection from the bundle. We can put like phi, call phi the natural projection over U, and we can restrict phi to this map from the Nash modification to X. All right? This bundle, if we restrict to the Nash modification, we still have the structure of a bundle. So let me put like T tilde to be the restriction. All right? Fine. Okay, so this is a diagram that we are going to use to define the local obstruction and two other elements. All right? It's going to appear in my talk. So the strategy is the following. We start with one differential form in Cn. And then through phi, we can consider the pullback of this one differential form over this Cartesian product. All right? And then we can restrict it to the Nash modification. Omega tilde would be the restriction of this. No. The restriction of this pullback. All right? So this one differential form over the Nash modification is a section in the dual bundle that we saw in here. The bundle has a name, is Nash bundle. So, so this is a section in the dual Nash bundle. So I'm taking a small epsilon where this section is non-zero over a sphere, a small sphere, centered at the origin, and we reduce epsilon. All right? And then let us denote like this the obstruction cocycle to extend this one differential form from the sphere into the ball. All right? Associated to this element, to this cocycle, we have a fundamental class in the homological group, the corresponding homological group, and then we can make the evaluation from one to another, right? And then this evaluation gives us an integer number. All right? This is the strategy. When we take W, or omega, I already said omega, right? So if we take omega to be the differential of z bar, here we have this z bar would be like this. All right, so if we take omega to be this one differential form, then what we get in this evaluation is the local Euler obstruction. All right? The local Euler obstruction, Thais said to us that it's not easy to compute, and I'm sure that this obstruction can prove that to you, right? At least to convince you of that. And it appeared as an important ingredient in the proof of the Grothendieck conjecture about the existence and unicity of Chern classes for singular varieties. Right? This is not new because she already told that to us, but still is the local Euler obstruction. In 2004, Bracele and Seade used this diagram to introduce a similar object, but what they made was pretty impressive. They construct a vector field using function f. Let me just put here. So we have a function f defined on X, our complex analytic space, with isolated singularity at the origin. Singularity at 0. So they construct a vector field, and using the gradient of this function, and they obtained by following this construction. So looking at the pullback by this projection, restricting to the Nash modification, and evaluating the obstruction to extend, to make the extension needed. So they used that one differential form to define the Euler obstruction of a function. So using the same strategy, but with the correct, the good one differential form, the good vector field, they defined the Euler obstruction of a function. And the impressive thing, in my view, the impressive thing is that using that good vector field, they get this relation between the Euler obstruction of a function and the local Euler obstruction. All right? So what they proved is that the Euler is the local Euler obstruction minus this summatory over here. In here, I didn't write, but VI here are strata of a Whitney stratification. All right? Good. And here we have also the Euler obstruction of X at a point of a strata of that stratification. Okay? The thing is that this singularity that we have here might be degenerated. So in 2005, Seade, Tibar, and Verzobelsk proved that if we have this degeneration, I'm saying is in terms of the Hessian matrix itself. All right, is the way we are habituated to talk about. So if we have the Hessian matrix associated to F at 0 to be singular, then we have a degenerate singularity at 0. And what they studied is that if we take a deformation of our function, like this, T would be a complex number, and L will be a linear function. So if this function, if L is generic enough, we can use this deformation to produce only non-degenerated singularities. All of them contained in the regular part of X, in the regular part of our space, right? So they not only prove that this is the type of deformation we need to use to produce only a finite number of non-degenerated singularities, but also that number equals to the Euler obstruction of a function.
You can also have singularities in non-dimensional space. But this only sees singularities
At the regular space. Okay. Okay. Thank you. Okay. So, all right. So this is what happens. Now, moving forward to the Charn obstruction, we still are going to use this diagram, but instead of starting with one differential form, we will start with several differential forms. And what we are going to do is pretty much the same strategy. But the difference is that we need to not consider only one Nash bundle, but as many bundles as we have of differential forms, all right? So we have several differential forms, and then for each one, we consider the appropriate bundle, all right? This construction we are doing here is we need to use the germ idea. So we are working in a neighborhood of a singularity, right? So if we are changing the differential form we are changing the object, we need to change also the notion of singularity. So singularity in this setting would be the following. We consider an element in the Nash modification, and a special point, a singular point, will be the one where we restrict each set of differential forms. We restrict to this T, this limit of tangent spaces, and we need to get linear dependence. All right, this is it. So instead of calling a singularity a critical point, Ebling and Seade called is over here. All right, and then we can proceed with the same strategy, and we look at the extension from the sphere into the ball for all the one differential forms at the same time. And what the number that we get doing this process is what Ebling and Seade called the Charn number, the Charn obstruction of this collection of one differential forms. All right? Similar to the case where we have only one differential form or only one function, we can talk about the degeneracity of that singularity. Here we also can talk about this degeneracity. The setting is the same. We consider the Hessian, it's a big Hessian matrix with using all of these differential forms, and then we can also have the special point to be degenerated, all right? So actually, Ebling and Seade wrote kind of 3 or 4 papers on this matter. So in one of these papers, they studied this deformation of the collection of one differential forms here that produce only non-degenerated special points, all right? So over here we have an element in the set we started with, and lambda would be a complex number, and Lij would be a linear function. Yes, right, a linear form. So they proved that, and this is correct. I mixed up with the other deformation, and I'm going to explain now, Professor. So what they proved is that if we do this type of deformation, you produce only a certain number of non-degenerated special points, all of them contained in the regular part of X. This is correct. In the previous, I was wrong. So this is why I mixed up. Here, this is what happens. And they also proved that the Chern number is the number of non-degenerated special points, all right? This is pretty similar to the work that Seade, Tibar, and Verzovix made. So the interpretation is pretty close. So this is why we asked if there was a setting where these two elements, the Euler obstruction of a function or the number of critical points, would coincide with the number of special points, all right? And the answer was yes. This is something me and my collaborators are still working. We are still working on that, but we got some answers that I want to share with you. So we started with the following collection of one differential forms: df1, df2. Let me say who is f. I'm sorry. I'm moving to here. So we have f1 and f2 functions defined on a complex analytic space. And the collection of one differential forms we are using is df1, df2, and a certain number of linear forms, linear functions. D here is the dimension of the variety, all right? So using this omega over here, we could prove that the Chern number of this collection of one differential forms is a number of Morse critical points. Not which one, which number of Morse critical points. The ones, when I say Morse, I mean non-degenerated, all right? Is the number of Morse points of f1, one of the functions in this setting, in this set, all right? The regular part of X intercepted by the inverse measure of delta by f2, all right? It is true that it's not any f1 and f2. F1 and f2 need to behave well with respect to each other. And the condition that's going to assure us that is the tractability condition. This means that when we look at this set, the critical set of f1, f2, restricted to a strata. We are always working in the stratified sense here. Out of the zeros of f1 and f2. So when we look at the closure, the dimension of this set, the dimension is at most 1. This is why Aurelio's talk was super interesting for us, because it's pretty close, right, to the type of condition. And also, when we look at the critical set of f1 and the zeros of f2, this is at most the origin. All right? So when this happens, we can compare these two numbers. And also, after a while, over here I'm working in the delta fiber, but we also have the same results when we have the zero fiber, right? We still have the comparison between the Chern number and the number of Morse critical points, all right? This number of Morse critical points that appeared over here is the number that appeared in Seade, Tibar, and Verzovic's work. So we have a pretty equality between the Chern number, the Chern obstruction, and the Euler obstruction of a function, all right? Okay. This result over here It was a joint work with Lima Pereira and Professor Maria Ruas from São Carlos, from USP São Carlos. And Lima Pereira, Barbara, is a specialist in the relative, in Bruce Hubbard's number in general, in ICES in general. And we were able to use this specialty of Barbara to find a relation between the Chern obstruction and the relative Bruce Hubbard's number. I mean, the gain when we look at the relative Bruce Hubbard's number is that we have an algebraic characterization for these topological elements that are, all of them are not easy to compute, right? But I need to be fair to Eblin and José Seade because they gave an algebraic characterization using indexes of vector fields, indices of one differential forms, right? But still, I want to show the result we get. So let's theta x to be the module of vector fields that are tangent to our complex analytic space, and the relative Bruce Hubbard's number. Yes, the relative Bruce Hubbard's number, sorry, I'm nervous, is this complex dimension of this quotient, all right? Ix over here is the defining ideal of X, all right? And then what we proved is that we have this equality. The Chern number of this form, this collection of one forms, is the difference between these two Bruce Hubbard's numbers, relative Bruce Hubbard's number, where over here we have F1 at this space, restricted to X intercepted by the zeros of F2, and L over here is a generic linear form. So if L is generic enough, this is the difference we get, all right? We have a condition on a specific condition on this module, all right? I can show you the specific condition, okay? All right, and then as an application, I want to just show you that if we change the type of collection of one differential forms that we have, we gain other types of invariants, right? So if instead of this collection, we have df1 and df2 in the first collection, and df1, the delta, where delta is the determinant of the Jacobian matrix of the map F, then we can use the Chern obstruction to compute the number of cusps of a perturbation of F, all right? So the Chern obstruction can be computed using the number of cusps plus the Milnor number of F1. All right, this is a formula that Bracele, Ruas, and Grulha already proved. So this is only another way, we gave another way to prove the same formula. All right? So this was my talk. Happy birthday, Pepe.
Are there questions? So we thank this.
Yes. Yes, we can use your work with Tomasella and Bruna. And there is a characterization there using a finite functions, a finite maps, right? And then with that characterization, we can use the Chern number also to compute the number of cusps. And in that case, we still need a partial. One of the partials is the index of the collection of forms. But we do have a result on that matter.
Just a comment, it's not a question. It's the Euler obstruction is associated to is like an index of a section of a bundle. Just like with a vector field, you lift it to the Nash blow up, and then you have this Euler obstruction, which is associated to one section of the Nash bundle. So morally, that corresponds to taking the top Chern number of a bundle. Okay. Now, when you have for example, a tangent bundle of a manifold, you have other numbers, other Chern numbers. You have Cn, but you have also Cn minus 1 times C1, Cn minus 2 times C2, and so on. Well, to get those numbers, what Evelyn and José Seade do is that they consider these collections of forms. So those indices that they have actually corresponds morally to taking these Chern numbers. The original one corresponds to Cn, and then these numbers correspond to taking these other Chern numbers.
I see. I didn't know that.
No,
It's very, very interesting. Thank you.
No, pleasure.
More questions? So we thank the speaker again. And we'll be back at approximately 10 minutes. we're going to continue with a talk of Agustin Romano about reflexive modules on quotient surface singularities.
Hello? Yes. Well, thank you very much. Well, I'm very happy to be here. First, I want to thank to the organizer to the opportunity to give talk in this wonderful Congress, and of course, happy birthday, Pepe. And I am very happy to be here. I have been working in this kind of problems since my PhD, and that was some time ago. And this is our most recent result, and this is a collaboration with José Antonio Arciniega and José Luis Cisneros, and I don't know if is he? He's there. And so, what is the idea of this talk? What is the main objective? Well, in this talk, I will show how we classify the reflexive modules over a quotient surface singularities. This problem was open. It was the remaining case in the classification problem of finite. I will explain everything in a moment. And we found that the way to complete the classification of this theorem was by using the Tilla-Patoudy-Singer theorem. So we found a way to start to use this kind of machinery in singularity theory, and then we found an application in this kind of problems. So the main objective of today is I will show the general idea of how we did everything. For that, I need to, yes, with José Luis and José Antonio, and for that, I will use everything. So for me, I always work in this case, in this talk, with two-dimensional quotient surface singularities. So, and I will write in part. For me, X is going to be a surface singularity and an isolated surface singularity, and it's defined by just taking a finite and a small subgroup of GL2C, and then we take the quotient of C2 by the natural action of gamma in this space. So in this talk, I always denote by X is going to be always a quotient surface singularity. And now, small? Small is just that the only fixed point of the action is the origin. It's the only fixed point. And that is exactly the same as saying that when you take the quotient by gamma, the only singularity is the origin. It's equivalent. So that is, this kind of singularity, the quotient surface singularity, are already classified. The first classification, I think, that was done by Briscoe. Then there is another equivalent classification by Ramirez-Snyder. And this family of surface singularities is very well known to understand. No? Actually, you can look for the reference and you can find all the groups that are completely classified. And
if you ask to start at X be normal, you can remove the small.
If you, well, in what, I don't understand the.
If you already asked to have an isolated singularity, you can remove the condition of being small.
Well, yes, you remove only but if the singularity is normal, yes, the singularity is isolated. And then if the singularity is a quotient surface singularity, is the link is finite. So, okay, yes. Well, and then I will also use the link of the. And for that, I just need to embed the singularity X in some space. And using this embedding, I will denote always by sigma. Sigma will be the link. Since the singularity is isolated, in this case, the link is a three-dimensional smooth manifold, it's compact. And by Briscoe characterization of quotient singularities, the fundamental group of the link is finite. Important in a moment. And now, I will always denote by X tilde is going to be the minimal resolution. That is the actually, it's not really important to be the minimal resolution. Any resolution is fine in this case because it's a rational. But everything must with the minimum hypothesis, so just consider the minimal resolution of the singularity. Now I will, as the title of my talk says, I'm going to work with a reflexive module. So what is a reflexive module? So, Javier, there is the definition. Well, a reflexive module, a reflexive OX module is just a module such that the natural map from the module to its double dual is going to be an isomorphism. So in this case, reflexive modules are in this part of the board and are going to be reflexive if there are canonical isomorphic to its double dual. And this is the algebraic objects that I will use. And now let me fix some notation. The regular part of the singularity, I will denote it by U. I will denote by this the category of reflexive modules. So in this part, I have all the of the reflexive modules. I have the category of holomorphic vector bundles over the regular part. Because in the regular part, it's a smooth complex manifold of dimension 2. And now you can consider all the category of vector bundles over the regular part. And more, I have the category of the complex finite dimensional representations of the fundamental group. So remember that the link of the singularity. Yes, the link of the singularity. Yes. Yes, in this case it's actually gamma. Yes. And now I have two more objects that they are important, but I won't say too much. There is a way to define what is a connection over a module, and I will denote by this the category of pairs where M is a reflexive module, and this is an integral connection. And as usual, I have also the category of vector bundles with a connection, in the classical sense of a connection in a vector bundle. So with this notation, well, no, before that, these modules are, by definition, is an algebraic object, but if this definition is to algebraic, you can replace this for the category of bundles, because modules and the vector bundles over the regular part. So the reflexive modules in the regular part is shift sections of some vector bundle. So, and that's why this category is actually the same, reflexive modules with an interval connection is the same as the category of vector bundles with an interval connection.
So you actually define integrable connection on similar varieties, or just take the definition?
Now, there is a way to define what is a connection in a singular ring and what is an interval connection in a singular ring. Yes, but since we have this equivalence, and I think that for the bundles is classical, I think that it was not necessary.
So what you say here is not reduced to form singularity, it's true for any normal surface?
Yes. For in these slides, yes. Yes, this is true for dimensional normal. And actually, for higher, yes. For higher dimension, in the higher dimensional case, if the singularity is isolated, this part, the category of maximal Cohen-Macaulay modules, coincides with the category of vector bundles on the regular part. This other part is false, because for higher dimensional case, the category of reflexive modules is not the same as the maximal Cohen-Macaulay modules. Any maximal Cauchy-Macaulay is reflexive, but the converse is false in general, in higher dimensional case. Yes. Are not the same. Yes. Now, let me go one more. So, everything is because of this diagram. Well, in this diagram, I think that I can find everything, and many of the problems that I have been working in the previous years can be stated in this diagram. So, in this part, we have the representation theory of the fundamental group of the link. In this diagram, everything in black is true for any two-dimensional normal surface singularity. The part that is in blue is true because the singularity is a quotient surface singularity, and that was done by NO. So, in our problem, to classify the category of reflexive modules. In general, you can try to solve this problem for a normal surface singularity, and then you can relax or make the problem harder. Probably you want to classify the category reflexive module with an interval connection, and that is going to be the same as classifying the vector bundles. And there is a lot of questions that you can ask in this diagram. But for a quotient surface singularity, everything is in ISO, and then if we want to classify the category reflexive modules, it's equivalent to classify the category of reflexive module with an interval connection, or the category of vector bundles, or the category of representations. So now we have that our original problem has three different interpretations, and the three are going to be important in order to solve it. So now we can, and I will change many times between a reflexive module, and then I will take the representation because by no is a representation that corresponds. And I will use this kind of tricks in all the talk. I will clarify in every moment, but this diagram is going to be crucial. Now that we have the problem, yes? It depends on everything. Well, for example, no, this map, it's not hard to prove that in general this map is not injective. There is a way to produce examples showing that this map in general is not injective, and it was because of the theory, map should be onto, but was more or less hard to prove that was onto. There are like 3-4 different papers. They invented several algebraic invariants in order to find an example of a reflexive module that does not admit an interval connection. And that question was hard, but like 3-4 years ago, with an annual we found the first singularity and the first reflexive modules that does not admit an interval connection. And the answer was because we studied this problem in the category of vector bundles. So if you want to study when this map is onto, in general it's hard. It's interesting because these kind of objects cannot be detected with the topology of the singularity, but in general it's hard to produce examples. And now it depends a lot of things. Probably if you want to study the moduli space, probably you want to study this category because, well, this part, because this is the algebraic part. If you want to study the deformation that is topological constant, probably you want to study this object. So it depends a lot of what do you want to study. Yes, in some sense, yes. We found, yes, the fundamental group is, but in general, this map is not an isomorphism. It's an isomorphism only in the case of a quotient surface singularity. So our example was a hypersurface singularity that was not, actually the example is not really hard. In the x2 plus y3 plus z7, in this singularity, you can find reflexive modules of rank, well, vector bundles of rank 1 that does not admit, non-trivial, that does not admit an interval connection. And well, we have, with an annual down, we found families of singularities. So, and that can, yes, yes, yes. And actually, yeah, of our example, the origin, because in the length is an integer homology sphere. So there are one-dimensional representations. So one-dimensional representation, we only found one non-trivial reflexive this part. Yes. Yes. Good idea, yeah. So yes, this diagram is very interesting.
So that even in this risk or decrease.
Yes, in that case, yes, there are reflexive modules of rank 1 that does not admit an interval connections. So they are not coming from the full.
If you have something more cheaper, let's say.
Why don't we let him, he has only half an hour.
Half. So we want to classify reflexive modules. And well, it is only on the singularity level, but we have the resolution. So there is a way to state the same problem on the resolution. This is going to be easier, more or less, because in the resolution we don't have singularities. So the way to study this kind of problem is to introduce the notion of a full shift. A full shift is a locally free shift for the resolution. I will just denote by full this category. This is the it's just you take the pullback and then kill the torsion. For a quotient singularity, this is enough, and you can prove that this is actually locally free shift. Important thing is the following. Again, we have a one-to-one correspondence between reflexive modules and full shifts. And this is the way to go from one category to another. This category is also in a one-to-one. So again, we can restate the problem as classifying full shifts over the resolution of the singularity. And well, this problem is more or less solved. The first case, in the case of a rational double singularity, this classification problem was solved. Actually, this is like the first interpretation of the Mackay correspondence, and then later was reformulated by Artin and Berg. They solved this problem in that case. And NOAS, in general, if the rank of the first class of that are bundles are enough to solve this problem. And the answer was no. Wunram produced a counterexample, so he found two different full shifts with the same rank and the same first class, but they are different. And let me say something more about this counterexample. So you can look for in the Wunram's paper, the counterexample is at the end. The important thing is that the singularity that Wunram was using was a quotient surface singularity. He found two different vector bundles, full shifts. I think that the rank is 2 or 3, probably it's not, the rank is not really. And he found that they have the same rank and they have the same first class. Now consider the determinant bundles. The determinant bundles are rank 1 bundles, and they have the same first class as the vector bundle, as the original vector bundle. But quotient singularities are rational singularities. So for rank 1, we don't have moduli space, moduli. All the Picard is completely determined by the first class. So since these two line bundles has the first class, they have to be the same. This is one part. Now, if you check in the paper by Wunram proved that both, the full shifts appears in a short exact sequence as this one. Just the trivial one of the rank R-1, the full shift and the determinant bundle. There is a way to produce this exact sequence. It's in the paper by Wunram. Wunram did this computation. But now consider this observation. If you consider this as a singularity vector bundle, they are the same, because in this category, every short exact sequence of you can take a partition of unity, you and then you can produce this decomposition. And L1 and L2 were the same. So as differentiable vector bundles, they are the same, but as holomorphic vector bundles, they are different. And that's why this problem is hard, because we need to find an holomorphic invariant that detects the holomorphic structure. Any topological or infinitely invariant is not enough to solve this problem, even for the quotient surface singularity. In general, it's harder. And well, that is the problem, and that is the main difficulty of this problem. And well, some results for the rational double points solved by Arten and Verdier. In general, if the singularity is rational, in particular quotient surface singularities are rational, with Nemeti we classify but only rank 1 reflexive modules. We tried to use our program to classify more vector bundles, and it was impossible. Our paper works well for rank. Higher dimension, higher rank is difficult. And it's known that quotient surface singularities are the only singularity that has a finite number of indecomposable, the same as finite number of irreducible representations. These kind of singularities are called finite representation type. So we want to complete the classification in the category of finite representation type singularities. And how we solve it? That is the main, the most important idea in this talk. Well, the idea came from another paper, like probably 3 years ago, with something prepared on arXiv with José Luis Cisneros and also with José Antonio Arciniega. And in that paper, we noticed that there is a relation between secondary characteristic classes and the spectrum of the singularity in the case of a rational double point singularity. For that, we need to, in that paper, we developed all the theory of secondary characteristic classes on the singularities, and in that paper, we noticed also that there is a relation with the Tillet-Patodi-Singer theorem. And with that idea in mind, that the secondary characteristic classes are producing some invariants, probably new invariants, we want to use this as an implication, and we notice that the theory of secondary characteristic classes is enough to solve this problem. So, what is a secondary characteristic class? This is general, this is more topological. Consider L is going to be a smooth manifold, and over L, here a vector bundle, some rank, and with a connection. It doesn't matter. And using this connection, we can define the RAM classes. You can construct the RAM classes using the theory of Weil, Chern-Weil, and you can construct this logic. And we have this long of cohomology groups. In this part, you have the classical, the usual Chern classes, and it's very well known that under this long exact sequence that is coming from the exact sequence of the coefficients, the Chern class goes to the RAM class. This is true in general, but now suppose that the vector bundle, or well, the connection is flat. The vector bundle is a flat vector bundle, so the curvature is 0. Curvature is 0 is not difficult to prove that actually the Chern class, the RAM class is trivial. So this is a long exact sequence. You have the Chern class goes to 0. Then there is at least one preimage. Well, the secondary characteristic classes are the canonical preimage. The canonical means that satisfies a list of good properties with respect to functoriality. You can compose with differential maps and take the push bar and pull back, this kind of construction. can define the secondary characteristic class for non-flat vector bundles, but the definition is more complicated. Everything is in the paper by Chigger and Simons. For our case, this is enough. Now, consider just some notation. Consider again, L is a smooth manifold. Consider a representation of the fundamental group of that manifold, and you can associate a flat vector bundle that corresponds to such representation. Then I will just denote by this the secondary characteristic class of the vector bundle associated to the representation is just this symbol. Now, this is general, but now in our case, the link is a compact three-dimensional manifold. So suppose that this is a three-dimensional manifold, and using a universal coefficient theorem, we can imagine that the cohomology class as maps things. So some numbers. You take an integer class and you evaluate the secondary characteristic class in that, and now you put a number. It's a three-dimensional. The secondary characteristic class lives in H3, and consider evaluate the secondary characteristic class, and you put a number. So we have numbers. What is the meaning of that numbers? The first secondary characteristic class is actually computable. If you know the representation, this is the formula that, and you can compute the actual number. So the first secondary characteristic class is not really hard. You can compute the second characteristic class, second secondary characteristic class. That is the difficult part. In first paper, we proved that for our case, that the link is a compact three-dimensional manifold. The second characteristic class of any representation is the analytical invariant of the Tilla-Patodi-Singer theorem. So this is the way that we found a connection with the analytical invariant of the Tilla-Patodi-Singer. This is true for representation in SLNC. We have a formula for GL, but it's going to be harder, and that is more, I don't need it. This invariance of the link to on the resolution, there is a way. Can be computed over the resolution by this horrible integral formula. Right now, we don't have a simplification and more friendly formula. You can do it. The formula says that yes, you can compute it. So the main thing is that this invariant is actually computable in the resolution of the singularity. So now, and this slide is more or less the main idea. You have the quotient singularity, the minimal one. You consider a reflexive module. That one has a flat connection by by Hilbert correspondence. There is one representation that corresponds to that one. Invariant. That invariant is an invariant of the full shift, because the full shift has a unique flat connection, and that determines a unique representation. So this invariant is of the full shift. And our theorem says that two full shifts are the same if and only if the rank, the First-Chern class, and the X invariant are the same. So probably, how much? 1 minute? 2? 1. Okay. Just quickly, what is the main idea? How we solve everything? First, we have to use classification by Riemann-Schneider in order to compute the cohomology groups of the fundamental group of the link. So because by Riemann-Schneider, we already know what is this. We have the list of these groups, and now we have to compute the cohomology of that groups. Now that we have that part of information, we compute these invariants for the case of rational double point case, and using that information together with the point 1, we can compute the analytical invariant for all the quotient singularities. There is a way to do it. If you know the first span of 2, you can compute that invariant for almost all the quotient singularities. There are 2 exceptional cases where you have to do an extra work, but the extra work can be done with a formula of Gilkey. There is a way to compute the X invariant using a formula given by Gilkey, and with 1 and 2, you can complete and compute all the invariants. And actually, well, I have time, but actually we computed. We computed all the representations, we computed the formulas, and we actually know the numbers for all the quotient surface singularities. And using these numbers, it's more or less easier. I have time to be sure that they are always different. And, well, that's all, and that's all.
Questions? Questions?
PQR, sorry, for the Briscoe manifolds PQR, relatively prime homology sphere, you can obtain the invariance in terms of PQ and R?
We believe that yes. For some very concrete examples, yes, we have done the computation and we more or less know what is the numbers. And now we have two problems that is very particular for some numbers. We have a general algorithm for PQ and R. And the second main problem is that we have the numbers, but we don't have an interpretation of that numbers. We believe that because for our experience in the rational development case and these new numerical examples, we believe that this is more or less related also with the eigenvalues of the Milnor monodromy. But why, again, have no idea. We know because we have the computation and the computation agrees. And that's all. We have a geometrical meaning.
Thank you.
In the more complicated case, what happens when you just have several cells?
Well, even for the hypersurface singularity, if there's, for a very generic hypersurface singularity, the category of reflexive module is of wild representation type. So you can embed all the category of reflexive module in that category. So the classification problem is impossible to solve in general. That was, we proved that with Javier Fernández Bobadilla. So for a very generic, the picture is very horrible because the category is wild representation type. It's really big. So you can try to find some subcategories that are important for some sense, and there are some subcategories like specialty and something more, but it depends on what you want to study.
More questions?
Thanks. Can you put the slide with your index formula?
Yes. I think that this one?
That one, yeah. So first of all, I completely lost. What is a D?
I'm sorry, yes, D is the Dirac operator.
D? Ah, it's the Dirac operator. So, and here you have singularity. So, do you think this is a way to find the index formula in general for singular varieties?
What general?
Because for the moment there is no index formula for singular varieties.
Yes.
And this is one example where you give some formula.
Yes. This, I think that this is true for surface singularities where the link is a rational sphere.
Yeah.
I think that this is our most link is not a rational.
You don't know. Okay.
No.
Okay.
No. This is very particular because quotient.
Yeah.
Is for the link a rational homology sphere.
Okay.
And everything bigger than that, I have no idea.
Yeah, but because there are some people trying to find a more general formula, but using either intersection homology or non-commutative geometry and so on.
Yes,
So I don't know if
no,
it's on the way.
Okay.
One last question? No?
I think what Jean-Paul has in mind, if I'm not mistaken, is the general Atiyah-Singer index theorem for singular varieties. That's what you have in mind, no? I think it would be fantastic, but yeah. Thank you. Yeah. Yeah, I know. Thank you. Thank you.
So we thank the speaker again. and we come back in approximately 10 minutes.
No, it's not yet there. No, I think I see it.
You can see, you don't need I tell you 5 minutes before.
No, I think it's going to be a bit rushed anyway.
Okay. Okay, so we continue with the talk of Matthias Sack. He's going to talk about singularities in the search for an automorphism of an Enrique surface with minimal entropy.
All right, thank you. I hope you can hear me. All right. So first I would like to thank you for inviting me here. It's a pleasure. And also I would like to thank in particular Angel Cano, who I don't see. Yeah, the last 2 days I was unable to attend the workshop because I had eaten something wrong on Sunday. And he took very good care of me. So thank you, Angel. Let's have one applause for the support of the organizers. All right, so I want to report on our search for an automorphism, a very specific automorphism of an Enrique surface with minimal entropy, and this actually comes from dynamics. And I have very little idea about dynamics, but I would be very happy if you see any connection to other topics and talks of this conference to approach me, and I would be happy to know more about it. So this is joint work with Simon Brandforst from the University of Saarbrücken, who is the expert on Enriquez and K3 surfaces that will play a very prominent role in this research. So the starting point was the following theorem by Ogiso and Yu, and they prove this theorem, which says that there is an Enriquez surface automorphism which has this number as the first dynamic. Just any number, it's a Salem number, which is a little complicated definition that will come below. There's a proof of such an automorphism. So our goal is we want to find this Enrique, which is a complex surface. I will tell you the definition later. And this automorphism. We want to have it explicitly. So they prove existence, but they don't give you the surface. So a Salem number is a real algebraic number where the minimum polynomial may not only have tau as a root, but also it has to have the inverse of tau as a root, and all the other roots lie on the unit circle. It's a little awkward definition, or it was to in the beginning, but that's what it is. So the first dynamical degree, which might ring a bell to some people, is the maximum of the absolute value of the eigenvalues of the pullback of this automorphism on the second cohomology group. And then we say that F has positive entropy if this value is bigger than 1. Yeah, or if the logarithm of this is bigger than 0. And as a matter of fact, if such an automorphism does have positive entropy, then its first dynamical degree is Salem, comes with such a polynomial and so on. So this is the minimum Salem number is as the first dynamical degree of an Enrique surface automorphism. So I need to give you some background because I'm from singularity theory originally, and I guess many of you also are. So let me tell you first what an Enrique surface is. An Enrique surface is a compact complex manifold which has the first cohomology group of the structure sheaf equal to 0. And you also call this the irregularity of the complex surface. And then you have the canonical divisor, which must be non-trivial, but 2 torsion, which means that 2 times the canonical divisor is linearly equivalent to 0. That's just the definition. It is what it is. That's an Enrique surface. And as a matter of fact, the universal of an Enrique surface is a K3 surface. So in particular, the Enrique surface itself is not simply connected, but the fundamental group is Z mod 2. So this universal cover is a 2-to-1 covering map, and this X is always something that you call a K3 surface. So what is a K3 surface? A K3 surface is, again, a compact complex surface, but this time simply connected, right? It appears as the universal cover of something, better be simply connected. And this time with trivial canonical bundle. All right, so even though the definition seems rather mild, or the restrictions made by the definition seem rather mild, to me, what's interesting about them, they all look the same, right? For instance, the Hodge diamond always looks like this. So here's the H00 from the Hodge decomposition, here's H01, and here is H10, which is this cohomology. And here, this line in the middle, that's the second cohomology group, but separated according to the Hodge decomposition, right? And it always looks like that, and it continues to H3 and H4. So if you look at the second cohomology group, this Hodge decomposition works for complex coefficients, but if you look at the second cohomology group with integer coefficients, then you have an intersection form, the cup product, and you can choose the set of generators and do the gram matrix for this set of generators, and then you get what you call a lattice, right? Which is just an intersection form on a free Z module. And this lattice is also always the same for all K3 surfaces. Call this the K3 lattice, lambda K3. So how can K3 surfaces differ? Why is there not only one K3 surface? They differ in their complex structure. Or if you do it in positive characteristic, of course, in the algebraic structure there. So one more background information that I need to give you is the Torelli theorem for K3 surfaces, which says that two K3 surfaces, X and X prime, they are isomorphic if and only if there exists an isometry of lattices. So this is a free integer module 2. This is a free rank 22. And sorry, say again? Yeah, biholomorphic. Yeah. And an isometry is an orthogonal transformation between these free modules, which preserves this intersection product, right? And moreover, it has to preserve the Hodge decompositions. So if you have a biholomorphism between two K3 surfaces, then natural that the intersection product will be preserved, and it's natural that the Hodge decomposition will be preserved. And this Torelli theorem says that this is already sufficient to say that two K3 surfaces are isomorphic. And moreover, if you have such an isometry of lattices, and it preserves the positive cones and induces a bijection between effective classes, then it comes, in fact, from a unique geometric isomorphism of these two K3 surfaces. So why am I telling you this? All this says that a K3 surface, if you want to describe a K3 surface, you don't need to describe it in terms of equations or construction. The only thing you need to do is you need to give one vector in this complex vector space. And that's your K3 surface. And unfortunately, the proof by Ogiso and Yu, the result that I showed you in the beginning, it did not give a construction or anything. It gives you this, a vector in a complex vector space. And it says, here's, that's the K3 surface.
What's the dimension of this vector space?
22.
And that's the same dimension than the modular space of K3 surface?
Yes, I guess you can use this as a moduli space, right? But then For different points, you have an identification if there's an orthogonal transformation, and then you would have to glue, and it's nasty, right? So another upshot is that an automorphism of K3 surfaces can also be described just by such an orthogonal transformation which preserves this period, this vector here. And then originally we were not talking about K3 surfaces. So how do these enter the picture? Well, the K3 surface is a 2-to-1 cover of the Enriquez surface. So there's an involution of this covering, and this involution can also be described by such an orthogonal transformation. And if you want to describe the automorphism of an Enriquez surface, then, well, the only thing you need to do is describe this orthogonal transformation for the involution and the lifting of the original transformation to the K3 lattice above. And in fact, this is the output from Ogiso and Yu's paper. So the K3 lattice, then an automorphism of the K3 surface, an Enriquez involution, and a vector for the period. And we want to construct really an explicit K3 surface and an automorphism and an involution which do this automorphism of minimal entropy. So for a K3, how we do this? We need to get our hands on the second cohomology group, and this is notoriously difficult. So what we can do is we can get our hands on a subgroup which is Néron-Severi lattice. And this subgroup is spanned by the Chern class of algebraic line bundles or of divisors on the surface. This is the thing that we can model effectively in a computer, and we can get our hands on. And unfortunately, this is not everything, and the complement is called the transcendental lattice. So Ogiso and Yu have shown that for K3 surface in question, this transcendental lattice has a very particular form, and the automorphism that we search acts there with order 8. So we already know some things that happen there. I think so, yes. But I don't want to put my hand to the fire right now. But what happens is that, if X is projective, then the Néron-Severi lattice is again the complement of the transcendental lattice that should make it saturated, right? We can discuss later. Yeah. So we can recover the action of phi on this Néron-Severi lattice, and that's what Simon did. And the upshot is that we now will try to find candidates for the surface. We will try to find candidates for the automorphism. And we have this fingerprinting here, right? There's a fingerprint. If we are given an automorphism, is our automorphism is the action on the Néron-Severi lattice. No, on the first slide it was already. So the Ogiso and Yu paper said there is an automorphism of minimal entropy. That was their motivation, I guess, to find. Okay, I sweep some arguments under the table, but I can give them later. So the fingerprinting on the Néron-Severi lattice will be sufficient. And I will have to do a small commercial break because all of this is actually Simon's field of expertise. But we tackle this problem within our research project, which is OSCAR, financed by the Deutsche Forschungsgemeinschaft in this Sonderforschungsbereich. And it's a computer algebra system which incorporates many things that you may know. Here, for instance, Singular is now incorporated in OSCAR, Polymake. Maybe some people doing toric geometry have used Polymake. And it has a lot of nice features from group theory and number theory. And we try to build one big thing that can do everything. And together with Simon and Anne Frübis-Krüger, we are building a framework to handle algebraic schemes in OSCAR. And everything that you're about to see now is what we can effectively do with this package for schemes in OSCAR. So all the constructions, all the verifications we can do in this generality. So if you have problems where you think this could be useful, I invite you to talk about it. Julia is a programming language in which all this takes place, like Python or C or something. I have very little time. Can I tell you later? Open source computer algebra research. Okay. So how do we construct the K3 surface? The K3 surface from the paper by Ogiso and Yu, it already appeared in another classification, but also only in terms of a lattice and a period. But this is a classification of finite subgroups of the automorphism, finite groups which act faithfully on a K3 surface. And if you look in this classification, the reference will be on the end, then it's this entry in this classification. So the group in question can be noted like this. And then we look at the invariant lattice of this group action, right? So everything happens on the lattice theoretic side, so the group action is also given in terms of orthogonal transformations. And it turns out that the invariant lattice is spanned by a single divisor class, and the linear system of this divisor class has dimension 4. So that means we get a rational map from X to P3. And then further lattice theoretic observations by Saint-Thomas, they say, well, this linear system is actually base point free and hyperelliptic, which means we get a map from X to something that is isomorphic to P1 times P1 in P3. And this is a generally 2-to-1 map. So that's our starting point to construct the surface. And the matrix, the group G acts as a matrix group by these two. No, sorry. So we take this group, and then we look for projective representations on P3, motivated by this linear system here. And we find that there is a projective representation where the group acts as a matrix group with these two generators. And then we look at the relative invariance for this representation, and indeed we find something that defines our nice P1. Right? So here I try to draw P1 times P1 with the two fibrations and the projection here to one of the factors. And then we use the second equation to construct to construct a generically 2-to-1 cover, which is branched along the zero locus of this B. Right? So in a suitable affine chart of a suitable projective bundle, we set lambda squared equal to B to have a 2-to-1 cover, which is branched along B. And here I try to sketch the branch locus in red. So it turns out that this composition here with the projection to P1 is a genome. Well, the fiber here is just P1, which is topologically a 2-sphere. And then we have a 2-to-1 cover, which is branched along 4 points. And many of us, particular people like Brasselet, will know how to compute the genus of the surface upstairs, of the Riemann surface upstairs. There's a genus formula for that. So this fiber really has genus 0. So it's an elliptic curve, provided we can give a point on it, which must be the origin. So we can verify that what we constructed so far is indeed a K3 surface, and that it is our K3 surface follows from the fact that we can indeed lift this group action to the thing we constructed. And we can really do this in the computer. So we found the K3 surface. Then what also fell into our hands was the Enriquez involution here. It's just given by this, induced by this automorphism of the P3, of the ambient P3. And what we need is now a description of this Néron-Severi lattice. So we need to find as many divisors as possible on our surface. And we get this from reducible fibers. And that's where singularities come into play. So as I vary this, this family coming from the projection to P1, the generic fiber is a torus, but I might encounter singularities of this fibration. And this picture is a little misleading because what effectively happens is that the torus splits into a bouquet of spheres, right? And these spheres, they are new divisors which are more special, and we collect them to get generators for our Néron-Severi lattice. And then what we also need is a section or several sections of this genus 1 fibration, and there we make an ansatz with a tilted diagonal in P1 times P1, and then we, for suitable values of this parameter A, which twists the angle of this diagonal, then we see that the defining equation for the covering splits, and we find another couple of spheres upstairs. Okay, and then we can use the group action to get even more divisors, and we finally find the full Néron-Severi group. So what remains to construct is the automorphism. And we do this by by a technique that's called fibration hopping. So what we had here is not only a genus 1 fibration, but once we have a section, we get something that's called an elliptic fibration. And yeah, let me switch that one, skip that one. So an elliptic fibration can be thought of as an elliptic curve, but not over the complex numbers or the rational numbers, but over a function field in one variable. So that's the function field of the P1 on the base. So you get something like a Weierstrass equation, right? And only that the coefficients of these Weierstrass equations are now rational functions in an additional variable t. And from such a Weierstrass equation, you can take a suitable projective closure and then construct an elliptic K3 surface whose projection to pi1, I mean this comes from a projective bundle over P1 and has a projection to P1. The closure of this is what you call the Weierstrass model, and then you can compute a resolution of singularities and get a smooth surface X1 mapping to P1. And this is also something we can now do in OSCAR. We can compute a resolution of singularities. So what we did is first we construct this as something that maps to a quadric in P3, and now we reconstructed the same surface as an elliptically fibered surface, and we have to identify them via some isomorphism here. And even though this defining equation here is simple and the previous construction was also simple, this identification takes a horribly complicated expression, right? I mean, you see the dots here. If I expanded them, this expression 2 times the board. And you see the 16th root of unity, and you need to take several field extensions to make this possible. Only the t coordinate can stay. So now that we have our elliptic surface, we can take the divisor, which is given by the fiber of this elliptic fibration. And since we know how the Ogiso-U automorphism acts on the lattice, we can once. And we divisor, which is now called F tilde here. Yeah, this is the fiber of the original elliptic fibration. This is after acting once by the Ogiso-U automorphism. And this divisor determines another elliptic fibration, which is abstractly isomorphic to the first one, because it comes from an isomorphism. And again, with the choice of a section, we can turn this into a genus 1 fibration and actually an elliptic fibration, obtain a Weierstrass equation, Weierstrass coordinates, and rational chains of coordinates. And we get a rather nasty diagram. So up to now, we're only in this bit. So this is the first elliptic surface. This is the second one that comes out of F tilde. And here we have this change of Weierstrass coordinates, right? The coordinates, you need to write down the Weierstrass equations of both. So what you then do is we can bend this diagram to the right via so-called Möbius transformations, right? So we know that this fibration is abstractly isomorphic to that one. So in particular, the singular fibers have to be preserved. Singular fibers are special. They cannot be interchanged with smooth fibers. So the critical values are points in P1. And if we want to find an isomorphism of these two elliptic fibrations, there's only finitely many choices how to do an automorphism of P1 that takes a specific set of points to another set of points. And transformations, and then we can lift them to automorphisms of this. And then we make use of this. We choose one Möbius transformation here first to get back to our old fibration, to the old description of our elliptic surface. We then browse through all the remaining choices that we may have here for further Möbius transformations. And then the last thing that can still happen is that we have an automorphism of the associated elliptic curve over the function field that can come into play. But these are finitely many choices. And then we can go through these finitely many choices, and for every resulting map that we get over here, we can do the fingerprinting verification. We can see what is it doing on the Néron-Severi lattice. Is it doing the right thing? Is it our Ogiso-U automorphism? And yeah, the computer can help us to do exactly this. This part, I have no time. So there's a representing matrix of what it should do. And up to this point, we could find the Ogiso-U automorphism for a reduction of the surface to this finite field. But we're currently working on reproducing everything in characteristic 0, which is more complicated on the computer, unfortunately. But we're on it and we're optimistic. So that's it. Stop here. Thank you very much. And happy birthday.
Questions?
Are you planning to give equations for because you were constructing everything on the K3 side, right? Or are you planning to go to the British surface actually?
Yes, that's another task. I mean, honestly, we would be happy if we could construct the K3 surface and the automorphism explicitly. I mean, this automorphism is given in terms of rational functions, which are huge already. And this constructing quotients is in general very tedious, because when you have a scheme which is modeled by affine patches and their gluings, the involution might not be compatible with this patching. But in our case, we might even be lucky and succeed in giving the quotient as an actual scheme. We'll see.
Do you think it's possible to get a concrete example using a quartic? I mean, a quartic, a K3 surface which is a quartic, some beautiful quartic polynomial and automorphism, magic automorphism that produces what you want. You think it's a dream or maybe impossible?
That was our original guess, or Simon's original guess. He said, I saw this K3 surface already, and then it turned out to be a small mistake, and it's not a quartic.
Okay. Thank you.
So in the same ideas as Alberto, and double covers of cystic curve with simple singularities as the K3 and...
Yeah, I'm not sure, but I think also that is out of the picture. I mean, I would have to ask Simon whether there's a lattice theoretic description of when this is possible, but I'm afraid no. But elliptically fibered, it's nice, right? I mean.
So we thank the speaker again, please. And we come back in a few moments.
Oi, eu tenho que falar assim.
Fala um pouquinho mais forte.
Oi. Tá, então tudo bem. Eu vou conferir. Eu vou apagar a louça também.
Eso es como que, ¿no?
Não. Não, quero... Sim, espera. Aí, ok. Sim, pela luz. Tá dando pra ouvir? Eu tô falando baixo, mas tá... Ou ainda não liguei. Tá ligado?
Mas assim não.
Ok.
Precisa mais alguma coisa?
Não.
A gente começa...
Algo importante. No quiero...
Eu sei muito.
Você tienes que hablar con fuerza.
Ok.
Você ya es una autoridad en el tema. Tienes que creerlo y actuar desde ese espacio. Você ya no es una crianza.
Ok.
Profesor.
Ok.
Entonces actúa con fuerza.
Ok. A língua, eu estudei, mas o problema vai ser a língua. Mas, ok.
José tiene escrito muy bien escrito. Então,
Acredito
el
que
que no
sim.
entiende lo que José fala, no ganha.
A minha preocupação são as questions.
As perguntas.
Aí eu peço para falar em espanhol. Não tem problema.
Si você não entiende, disculpan, sorry, I don't understand. Con una sonrisa.
Ok.
Muy bien.
Tem meia hora de duração. Então,
Não, eu estou tranquila com o tempo. Eu acho que eu vou fazer menos. Então, como eu tenho mais minuto no tempo, mesmo a gente atrasando, não tem problema.
Tá bom, se você quiser, a gente começar na meia hora.
Ah, não. Como... Pode ser. Espera só o Pepe pegar um café e pode começar. Não? Eu tenho a impressão que eu falo assim, normalmente. Eu tenho que falar mais forte, então.
Um pouquinho.
Um pouquinho.
Tá com nervos?
Muito.
Não tem problema. Isso é muito boa. Vai ficar tudo bem. Tudo bem.
Agora sim? Perfeito. Gracias. Pela língua, não pela matemática. Ok.
Primeira vez que eu ouvi uma palestra, era uma conferência internacional, mas alguém veio com a ideia de que cada palestrante queria falar a própria língua. Eu adorei. Eu saí falei português.
Sem perguntas, né? E aí também não tem pergunta. A hora? Eu creio que essa hora. Como 1 minuto.
Você vai dizer o que são...
O que são? Acredito que sim. Acredito que sim. Não sei, é o mesmo Stanley ou é o anjo? Não sei. É o Sanfer. Estou.
So maybe we can wait for Artal. Yes, just one. Well, welcome to the last session of the morning. For me, it's a real pleasure to introduce our next speaker, Michelle Morgado. Me desculpa. Michelle is going to talk about the integrated equivalent Miller number. Michelle, thank you very much.
More strong? No. Okay? First, I'd like to thank for the invitation. It's very important for me to be here in this event in honor of Professor Seade. I don't speak English, and I hope everyone understands my talk. A little bit about my story with him. I met him at a workshop on Singularity in São Carlos in 2000. In 2007, I participated in a congress here in Cuernavaca, LeFest. I amazed everything here. In the next year, the opportunity of Professor Seade to be my co-advisor. Since then, I have learned a lot of mathematics with him. We have done interesting works together. Thank you very much. Congratulations. I decided to talk about a recent work. It's don't work with him, but it's involved minor classes, and I studied this with him. My talk is part of PhD thesis of a student of Anivaldo Grulha, was co-advisor. This is in the equivariant context. Equivariant theory is has been a central topic of study in mathematics. It is powerful for investigation and has been explored in many areas. Using the words of Omoto, Roberts, para os desempregados, we establishing a relationship between the equivariant characteristic classes and a equivariant Milnor number type of a specific case, singular hypersurface. Okay? Then the goal is to present the equivariant characteristic classes already defined, the equivariant Chern classes and equivariant Schwarz-McPherson classes. Next, talking about the para os desempregados theorem. This is the inspiration to define the integrated equivariant Milnor number, the title of my talk, and the equivariant Milnor classes. Okay? I just present this objective without details, okay, many theory. Okay, so let's start. We need a cohomology group in this context. This is project limit of a project system. To understand this, I start with a set of indices. Okay? The setup is G is a complex reductive algebraic group. This means we have a instruction of variety. Some X variety. Action For presentation is the application from to this the invertible linear application. This induces a natural action in this way. Use. Okay. More. Invariant. If this occurs, then those two. This the maps between G varieties is equivariant, preserve the action. Okay. The last one is X is, again, is a geometric quotient of X by G if this application satisfies some conditions. I talk about this. Okay? Okay, let's go. For representation, I say just V. It's possible in the collection of these opens in this way is the set of indices denoted by D, EI. In this set, we consider an order in this way with this order for each things. Sorry. The control of the combination exists, sorry, de equivariante linear inclusion. Exato. For elements in the set, we can obtain this map where this is the geometric quotient of X times U by G is this definition. Okay. So is to construction a project system. Okay. This induces this homomorphism, and this is a project system. The project limit is the equivariant cohomology group of X with respect to the group G. Okay? And this is the denotation. Now, to the next equivalent characteristic class, we need work. Yes. Sorry, aqui. Here. Perfect. We need to work a vector bundle in this context. Then consider a G equivariant vector bundle. This means the spaces are G varieties, the morphisms is G equivariant, and the action preserve the fibers linearly. Okay? Again, we construction a project system. For each open, this induces this vector bundle and take the usual chair classes of this bundle. The collection is a project system, and the project limit is the equivariant chair classes. This is an element of the equivariant cohomology group. Okay? The first, equivariant characteristic classes. Before the next slide, I note the similar construction is possible to the homology group and the group of the construction function. It's necessary to extend the classical McPherson transformation. Okay? The difference, I don't define this construction, but is the system is a direct system, and we take a direct limit. Okay? Before, I didn't define this, just present its idea of the work, the divulgation. We need 3 objects to define the next equivariant characteristic classes without details. So, first, for each open, consider the inclusion and consider we obtain this application. Here is not the equivariant group of the construction function. Is the group usual of the construction function using the function G invariants. Okay? The second object is the usual, classical McPherson transformation, the map that satisfies, talk about this, other peoples, the Delig-Grothendieck conjecture. Here, apply in the geometric quotient. And this special vector bundle, defining this way. It's called, it's all complex. Exactly. In this vector bundle, take the chair classes, and this is the map. The chair classes, inverse chair classes of this vector bundle, copy this composition. Okay? this collection is a direct system, and the direct limit is this homomorphism. I don't explain this because I don't define this. No, here this is G equivariant group of the construction function, G equivariant G group. Okay. I note this is the extension of the classical McPherson transformation given by Omoto in this theorem, in Portuguese. This, in particular case, if X is non-singular, we have the description as the usual, using of tangent bundle of X. Then the G equivariant Schwarz-McPherson classes of X is defined the same way. Okay? Then the equivariant Schwarz-McPherson classes extend the equivariant Scher classes. Okay. The natural next step is defining the equivariant Fulton-Johnson classes, define the equivariant Milnor classes. But it's not possible for us. We tried it, but using the inspired by Parsons-Pragas theorem with equivariant Milnor class directly. The case of singular hypersurface. Then I present the elements to understand this theorem after extend this. Okay. The setup is X via compact, non-singular, analytic, complex, variety of pure dimension n. L is a holomorphic line bundle over X. S a holomorphic section of the line bundle. Is Z of the zeros of S. Z, then Z is a hypersurface in X. Okay. Then we can consider two functions. This using the Euler characteristic of the Milnor fiber, and this describing this way using this map before. Okay. It's known of the classical theory. The Euler characteristic is constant across on the strata of a Whitney stratification of Z. Then use this notation. Mi S, the value of mi on the strato S. With this element in range, we define this number. Start with the biggest strat and recursively in the decreasing dimension the others numbers. Then this is the Parusinski-Pragas theorem. Describes the Milnor class of Z in this way, using this number, the chair class of the line bundle, and the Schwarz-McPherson of the stratum.
What is the meaning of that?
I don't know. No. Milnor classes up to psi is the difference of Fulton-Johnson class and Schwarz-McPherson classes. The description is important because it don't have Fulton-Johnson class in this description. This is great, okay? Then extend these elements in this context, equivariant context. appear this number, okay? Okay. For each point of X, it's possible describe Z locally using the Jeremy's on V, G equivariate. Then it's possible to define a mapping, the character of corresponding representation. I identify to. This means take a trace of the representation. Okay? The matrix spaces. Okay. Now, using this, you can define the equivalent Euler characteristic of the Milnor fiber, not in general. In this way, using this map. Okay? It's not a number as a usual case. It's a map. Okay? Now, I restrict my the information. I take G affinity group and consider the same application, this contest. The function using now the equivariant Euler characteristic and this describe the same way using the before. Okay. Some description about this. First, there is a relationship between the equivariant Euler characteristic and the usual Euler characteristic. Is this. And using the description by David Massey that describe the Euler characteristic of the Milnor fiber using of the Lie number associated, we have this description. Then, using this and these computations, we have this description, this sum in this way. Then we have the integrated equivariant Milnor number. Okay? Describe in this way. Okay. I studied this. In the particular case, if Z has isolated singularity, we have just one Lie number. It is the Milnor number. And therefore, we have this description, more simple, using the integrated equivariant Milnor number, using the Milnor number of each germ. Okay? There is a equivariant Milnor number. And what is the relationship? This is relationship. This number, the integrated equivariant Milnor number, is described in this way using the equivariant Milnor number by Roberts, where this is the determinant of matrix which represents the action for each element of X. Okay? Some results. If point is regular, this number is 0. H, this number detects the singularity. And this number is constant across of the strata in the Whitney stratification. Then we can define equivariant Milnor classes the same way. Now we have some modification, the setup of the Paruzin-Spragatz theorem in the equivariant context. Now, X is a G variety variant and S is G equivariant 2. Okay? In this context, using the result that this number is constant on the strata of a Wishner stratification, denotate this the value on the strata S, we have the same name in this context. Okay? Then we define the G equivariant minor classes in this way, the same. Okay? Using the number, defining now, the equivariant R class of the line bundle, and the equivariant Schwarm-McPherson classes of closure of stratum with the corrector, the order of the group. It's necessary G is a finite group. Okay? To finish, two results about this. The class has support of singular set, and the particular case, if X has singularity, we have just one classes, 0 classes, and this is the sum of the numbers, the integrate equivariant Milnor number of each singularity with this. And thanks for your attention.
Any questions? No? Well, Michelle, thank you very much.
Funcionando os passos das diferenciais.
Sim. Sim.
Muito bem.
Ninguém me fez perguntar, nada e me perguntou. Estava-se muito.
Não, mas foi muito forte. Eu gostei muito. Tem escrito esta coisa no artigo? Assim?
Ainda não está.